In this video, we're going to talk a little bit about something called measure theory. And measure theory is about how you assign to sets of real numbers or subsets of Rn a measure of the volume of that set. So in R1, the real numbers, we would be assigning lengths to subsets of R. And when we're talking about R2, we would be talking about area. So in this video, we're going to talk about sets of measure 0, and then we'll talk about the general measure theory. So the concept of measure is based on the length of an interval. And whenever you have an interval, like a finite interval, like a closed interval or an open interval from A to B, or a half open interval, in all these cases, we define the length of the interval to be B minus A. And we also include infinity and negative infinity as possible endpoints. So if you have an unbounded interval, you would just define the length to be infinity. Now we can define a null set. So a null set, say A, a subset of the real numbers, is intuitively, it's a set that can be covered by intervals, by a countable sequence of intervals, a countable sequence of intervals of arbitrarily small length. That's intuitively what it means. So more precisely, we say that A is null if for every real number epsilon greater than 0, there is a countable sequence I1, I2, ... of intervals such that A is contained in the union of the intervals, so the intervals might not be disjoint. Okay, A is contained in these intervals, and the summation of the lengths of the intervals, so summation from 1 to infinity, is less than epsilon. So a set is null if for every epsilon greater than 0, there is a countable set of intervals that such that the union contains the set and the total length. So if you take the intervals and then add up the lengths of all of those intervals and then add them up, it's less than epsilon. Right? And this is an infinite sum. The sum needs to be less than epsilon. Okay. So for example, any one element set is null. Why? Because if you have a one element set X, so a set containing a single element X, this is going to be contained in the interval from X minus epsilon over 2 to X plus epsilon over 2. Right. So countable means, in this case, finite or just countably infinite. So you have something like this, and then the length is less than, oh, well, in this case, the length is equal to epsilon. So I guess, okay, x minus epsilon over 3 to x plus epsilon over 3. So this has length 2 over 3 epsilon, right? Which is less than epsilon. More generally, any countable set is also null. So here, again, I'm using countable to mean finite or countably infinite. So a one-element set is a countable set. Okay, so why is it true that if you have a countable set, it is null? Well, so suppose that your set is A. So proof. Since it's countable, there is an enumeration. So enumerate the elements of A as, say, x1, x2, x3, dot, dot, dot. In other words, just take an explicit bijection from the set of positive integers to A, and then let xi be the image of I. Okay, so you have an enumeration of the elements of A. And the trick is, so basically, you want to take, for each point, an open interval such that the infinite sum is less than epsilon. So the trick is, so let epsilon be greater than 0. And for each I, let I sub I be the interval xi minus epsilon over 4 times 2 to the I, comma, xi plus epsilon over 4 times 2 to the I. Well, then clearly A is contained in the union of the INs, right? Because each I is contained, okay, because each xi is contained in II. And the summation of the length of the INs is equal to, so the point is that each of these intervals has length epsilon over 2 times 2 to the I. Or, well, okay, I'm saying with respect to n. So if that, and then that is epsilon over 2. That is epsilon over 2 times the sum, n equals 1 to infinity, of 1 over 2 to the n. And that sum is one, so you get epsilon over 2, which is less than epsilon. Did I do that right? I think I did that right. Yeah. Anyway, the point is that you can get a geometric series so that the sum of the lengths is less than epsilon. Okay, so any countable set is a null set. More generally, so a countable set is just a union of, it's a countable union of one element sets. Right? So more generally, suppose that you have a sequence n sub little n. So this is a sequence of null sets. Then their union is also a null set. Okay, let's prove this. So let epsilon be greater than 0, and we're trying to find a sequence of intervals that contains n such that the sum of the lengths of those intervals is less than epsilon. Okay. So since, let's see. So since n1 is null, okay, there are intervals I sub 1 sub k, or I to the 1 of k sub k for k greater than or equal to 1, such that the sum, see, the point is that we're going to sum over all of this. So we want this to be, say, epsilon over 2. So such that the sum from k equals 1 to infinity of the lengths of I sub 1k is less than epsilon over 2, right? Because we can do this for any epsilon, in particular epsilon over 2, and such that n1 is contained in the union of the I superscript 1 sub k. And in general, so n2, we can do the same. There is I subscript k superscript 2, k greater than or equal to 1, such that summation of the lengths of the I k2 is less than epsilon over 4. And you see what's going on here. And such that n2, of course, is contained in the union of the I k2. And so in general, for n, let's see. I guess for n sub maybe n, there is I k n, k greater than or equal to 1, such that the sum of the from k equals 1 to infinity of the lengths of I k n is less than epsilon over 2 to the n, right? And so now you have this countable, so you have this countable union, because you have each of these I superscript I, so I superscript 1 sub k, okay, for k equals 1 to infinity, that's a countable set. And then when you have I superscript 2 sub k for all the k's, that's a countable set. And you have this countable set. So the union, let's see, so the set, okay, let's say, of I sub k n, where n is greater than or equal to 1, k is greater than or equal to 1, this is a countable set. Okay. And if you take the sum of all of these lengths, so n equals 1 to infinity, k equals 1 to infinity, okay, you can add the lengths however you want, because these are, you're adding positive numbers, right? So the sum of the lengths of the I k n is less than epsilon over 2 plus epsilon over 4 plus dot dot dot, which is epsilon. And n is contained in the union of the I k n's. So that's the proof. So any countable set is a null set. And when we talk about measure, we'll see that the null sets are precisely the sets of measure 0. So maybe I should have called this video null sets instead of sets of measure 0. We'll talk about the outer measure in a different video. Okay, so every countable set is null. Now, can there be anything else? Can there be any other set that's null? Yes, you can have an uncountable set that is null. So a good example is the Cantor set. So I'm not going to go too into the details of how you know it's uncountable, but let's just define what it is. So the Cantor set is, you start with the closed interval 0, 1, okay, and then you remove the middle third. So then you have 0 to 1/3, union 2/3 to 1, and these are the closed intervals. And then you remove the middle third of each of those two intervals. So remove the middle third of each of these two intervals. And then that will give you 4 intervals, and you will have 0 to 1/9 union 2/9 to 3/9 union 6/9 to 7/9 union 8/9 to 1. And you repeat the process where you remove the middle thirds of each of the intervals. Okay, so let's say after you remove the middle third of 0, 1, you're left with C1, and you start with C0, and then you have C2, and you just keep going, and you define, so you keep going to get a sequence C1, C2, C3, so you get C1 is contained in C2, C1 contains C2, which contains C3, which contains C4, ... and then you let C be the intersection of the CIs. And that's called the Cantor set. Now, the Cantor set is actually a non-empty set because, for instance, it contains 0 and 1. Right? It also contains the endpoints, like it contains 1/3 and 2/3, and it contains 1/9 and 2/9 and 7/9, so on. But it also contains points that are not endpoints of any of the CIs. So for instance, it turns out that 1/4 is in the Cantor set. So anyway, that's a non-empty set, okay? It's a closed subset of R. Well, it's a closed subset of the interval from 0 to 1, and because it's an intersection of closed sets, and since 0, 1 is a closed set, it's a closed set in Rn. The Cantor set is closed in R, right? Because the closed subset of a closed set is closed. And it turns out to be, so one can show that the Cantor set, so C is called the Cantor set. One can show that the Cantor set C is uncountable. I don't want to get into that in this video. Maybe I'll do it in a different video. Oops. Uncountable. Okay. And why is it null? Okay. Why is C a null set? So it's uncountable set, and I claim it's a null set. Well, the reason is because C. Okay, so these intervals, right? The CIs. The length, if you look at the length of C0, it's 1. The length of C2 is, well, it's 1/3 times 2 is 1/9. No, it's 2/3. The length of C2 is 4/9, right? In general, the length of Cn is 2/3 to the nth power. And so given epsilon, just pick n large enough that well, by L of Cn, I mean the sum of the unions of the intervals. Pick n large enough such so that 2/3 to the n is less than epsilon. Okay. Well, so C is contained in Cn. So the length of C so C is contained in Cn, and Cn is a union of intervals, and then the total length is, so Cn is, say, like a union of, I don't know what these intervals are called. Let's call them like I sub 1, 1, I sub 1, 2, let's call that one I sub 2, 1, etc. So Cn is the union of I sub n for some finite number of n's, okay, and we have that the sum of the lengths of the INs for all n, when you add through all n, is less than epsilon. So that explains why C is a null set. Because we've expressed C as a subset of a union of intervals such that the lengths of the intervals when you add them up is less than epsilon. Okay, so those are null sets, and we'll see when we introduce the concept of outer measure that these are sets of measure zero. So we'll talk about that. We'll define the general notion of outer measure of any subset of R in the next video.